नमस्कार मित्रांनो, I am Dr. Prashant Pawar. We are trying to make video lectures for the structural mechanics. In this, we are going to focus on indeterminate structures, and for our university, it's unit number 3. We'll be focusing on mainly structure which is actually indeterminate, where the number of equations are less than number of unknowns, and that's where we have to find out additional equations to get the answers of that. And here we are going to study the stiffness method today. Let's see, this is first lecture we are trying to record here, and I'm going to use front and rear camera. So the when I have to teach, I will use the front camera and then rear camera to write the documents. So let me start the lecture by taking the unit number 6. So stiffness methods for the beams. So if you see the syllabus pointers, the concepts of stiffness, linearly elastic structures, derivation of stiffness equation, then stiffness coefficient, and then use of this for the beams. That is what we are going to study. So to begin with, we are going to concentrate on how to calculate the stiffness, or how we get the stiffnesses. So before we go to calculation of stiffness matrix or stiffness coefficient, we have to understand that what is the stiffness, basic definition of stiffness. So how will you understand what is meant by stiffness? So that concept we will see. If you have seen in the static analysis, force is equal to stiffness into displacement. Force is equal to stiffness into displacement. And if you have to get the stiffness, so if you write in the notation, it will, if we say P is equal to force and then K as a stiffness and let's say delta as a displacement. So if you have to get the stiffness, then you'll have to make delta is equal to 1, then it will become P is equal to K. So we can say that, so definition of stiffness will become amount of force required to produce unit deformation. That will be the definition of stiffness. Is it clear? So with that, we can go ahead and say, if we have like similar to flexibility, here also you may have P of I is equal to let's say K of I and J, and this will be delta of let's say J. So if you can see, this will be like then stiffness can be written, Kij can be written as a kind of uh, Kij can be written as force applied in the I direction to produce unit displacement unit displacement in j direction. So that will be the definition of coefficient of stiffness you have to understand. And similar to flexibility, here we have to know that this how to calculate the stiffness of any beam. So if you we will take some example how will you calculate the stiffnesses. So for that you have to understand the basic concept of stiffness. So how it comes. So if you see, there will be only one formula required for the stiffness calculation, because we will be considering in the form of rotational stiffness. So if you can take basically a beam with both ends fixed, and if you give unit rotation in at A, so you can call it as maybe theta A, and then it will produce a kind of movement, let's say m is equal to 4 ei theta A by L. Okay, so and then this side it will produce the moment as a m is equal to, it will be 2 ei theta A by L. And to make it as a stiffness, so this m is equal to 4 ei by L into theta A. So to make this m as a k, we will have to put theta A is equal to 1. So that way you will get k is equal to 4 ei by L. And so that way you can call it as maybe this end. So we will call it as a k11. So what is indication of k11? So if I call it as a 1 and if I call it as a 2, so then what will happen if I am applying the kind of unit rotation? So moment is applied at this end and measured at this end, so that's why it is a k11. So whereas k12, what is that? Rotation, unit rotation is applied at end 1, and what is the moment produced by that? That will be nothing but it will be 2 ei by L. Again theta A will become 0. So this is how we calculate the stiffness coefficient. So mostly we are ignoring, in case of stiffness method, we are ignoring the kind of ignoring the what you call axial deformation, and that's why it will have only vertical as well as rotational deformation. And how do you get the stiffness coming from the kind of rotational vertical deformation? It is from the sinking of support formula. So how do you get that? For example, this is a fixed beam, and suppose I want to find out the amount of stiffness or because of this unit deformation at this. So delta is equal to 1. So you know the it's a formula, so it is nothing but what is that? So it will be 6 ei. So it will be 6 ei delta by L square, and the other side it will be 6 ei delta by L square. So in this case, if we maybe call this as maybe 1 this end, this is the second rotational, and then vertical will be third direction. So how are we getting the stiffnesses here? It will be K13, that is because of vertical deformation is third here. Because of vertical deformation, how much movement is generated? So it will be K13, and that will be nothing but 6 ei delta by L square, where delta will be equal to 1, and that's why K13 will be equal to 6 ei by L square, 6 ei by L square. Similarly, K23 will also be K23 will also be like, what is K23? Because of the vertical deformation, which is, what is the vertical deformation? 3 is the vertical deformation, and what is 2? This is a movement generated at 2, so it will be again 6 ei delta by L square, and where again delta is equal to 1, and that's why K23 will become as a 6 ei by L square. So when we'll solve the example, you'll understand. So let me write the steps of solving the problem in the stiffness method. So what are the steps? We will note down one by one, and then we will able to solve the example correctly. Step 0, we can call it as a steps. We will write steps to solve beam problem using stiffness method. So let us label this as 1, 2, 3. So what is step 0? Let us call it as a step 0. So in this step 0, what are we doing? We are identifying degree of kinematic indeterminacy. So if you recall, in the flexibility method we were using degree of static indeterminacy, and here we are using something called as degree of kinematic indeterminacy or degrees of freedom. So step 0 is identification of degrees of freedom. So for example, let us take maybe 2 span beams, and we will understand. So if you take first example, let us say this is one example where there are 2 spans. Now this is a fixed part, so how many degrees of freedom are there? 0 here. So here how many degrees of freedom are there? We are ignoring axial, so there are, in the beam there are 2 degrees of freedom. One is rotational and another is vertical deformation. So this is here 0. Here there may be rotation. So if I label this as A, B and C, so here there will be rotation, and let us label this as a D1. Okay, and then here also there will be rotational degrees of freedom. Rotation is possible but vertical deformation is not possible. Here also rotation is possible but vertical deformation is not possible. So we call it as a D1 and D2. So there are 2 degrees of freedom in this example, and so if you call like theta A, what is here? Theta A is 0. So in this case theta B is not equal to 0, and that's why D1 is equal to theta B. And in this case what will happen? So theta C is not equal to 0, and that's why D2 is nothing but theta C. T2 is nothing but theta c. And similarly, if you take another example, let us take second example, so of two span, so where both two ends are fixed, and the middle there is a support, and if you call this as again A, B and C, so if you can see here, what is that, theta A is equal to 0, and here it will be theta B is equal to 0, not 0, theta B is not equal to 0, and theta C is equal to 0, and that's why here there is a 1 degree of freedom. So let us call it as a D1. So so here there is a 0 degree of freedom, here there is a 0 degree of freedom, whereas here there is a 1 degree of freedom. And what is that? D1 is equal to theta B. D1 is equal to theta B. I guess it's pretty easy to understand. Let us take one more example. So where we may have 3 degrees of freedom for the two span. Let us say this case. Okay. So what are the possibilities here? Let us say D1, D2 and maybe D3, right? Okay, so as far as our syllabus is concerned, we have up to 3 degree of freedom. So these are various possibilities. You can see theta A is not equal to 0, theta B is not equal to 0, and theta C is also not equal to 0. Let me say A, B and C, and in that case what will happen? D1 is equal to theta A, D2 is equal to theta B, and D3 is equal to theta C. So if you see here what has happened now, we can understand various examples how we can label. So if you say you can even take maybe 3 degree of freedom or something like that, more than 3. So we can have this 1, 2, 3. There may be this possibility also. So you can call this as maybe D1, this may be D2, and this may be D3, and here there is a 0. So let me label A, B, C and D. So in that case again theta A is not equal to 0, so D1 is equal to theta A, theta B is not equal to 0, so this will be D2 is equal to theta B, and theta C is not equal to 0, so D3 is equal to theta C. So this is how first step 0, where we label the degrees of freedom for each of the nodes. So this is very important to understand where are the degrees of freedom and where there are 0 degrees of freedom. Where there are 0, where rotation is not allowed, mainly fixed end, so there will be 0. So that so in this case, as this is a displacement based method, so first you will get answers as a displacement, that is rotations in this case. So let us go to step 1. So what is step 1? Again similar to similar to our this thing moment distribution method, etc. What we have calculated. Step 1 is again calculating fixed end moment. So fixed end moment calculations, fixed end moment calculations. So we have to find out fixed end moments and how to find out fixed end moment. So you are aware, but still some of the standard formulas if you want to recall. So if you have a W at the center, so it will be like a WL by 8, WL by 8. Then for the fixed be this thing for UDL, I guess it's a WL square by 12, WL square by 12, WL square by 12, and suppose if it is at W at A and B, and then you can have it as W A B square by L square, and then another will be W A square B by L square. So these are the standard formulas of fixed end moment. Then we have step 2. So once we take example, you will understand the steps. Whatever we have written steps, we will collect the steps from these papers, and then we will solve one example. So that will make you too easy for you to understand. Let's see what is the step 2. It is joint load. Joint loads is the step number 2. So in this case, what are we doing? Suppose if we take this beam and then if we have a, let us say, 2 span beam, this one, and then if we say this is maybe we will have to find out in this case how many joint loads will be there. As many degrees of freedom are there, that many joint. So I am taking maximum degrees of freedom for your understanding. So there will be D1 and D2 and D3. So there will be P1, P2 and P3. So 3 joint loads will be there. And if it is a fixed, it will get reduced to 2. If this is these 2 are fixed, it will get reduced to 1. So let us understand this. So let us say P1. So that is related to this. So it will be fixed end moment. How many joints are coming? There will be only one member is contributing, that is AB. So this will be fixed end movement coming from AB. So what will be P2? That is joint load here. So there are two members are contributing, that is BA and BC. So it will become PM BA plus PM BC, BA plus BC. So similarly, what will be P3? So related to this point, so it will become P3 is equal to, it will be CB, CB. So that's how we calculate the joint loads. So let us go to step 3. Once we calculate the joint loads, we will go to step 3, that is stiffness coefficient calculation or stiffness matrix calculation. So we calculate the stiffness matrix. So for all these 1, 2, 3, 4 diagrams, maybe few examples we will take how to calculate the stiffnesses, and that will help you to understand like for example, this beam, how to calculate stiffness matrix. For this beam, how to calculate stiffness matrix. This beam, how to calculate. And as I told you, the formula required for this stiffness matrix calculation is one is this. It's a very simple, 4EI by L and 2EI by L. So what is 4EI by L? If I am giving rotation at 1 and measuring movement at 1 or stiffness at same point, so giving rotation, unit rotation at same point and measuring stiffness also at same point, then it will be 4EIL. But if I am giving unit rotation at one end and calculating stiffness at other end, then it will become 2EI by L. It's a very simple 2 formula, and maybe this is another formula. So time being we will ignore this. This is mostly in the beams this part is not required, sinking of support. So only what we need in a beam, most of the simple problems, that is 4 EI by L and 2 EI by L. How to remember? 4 EI by L for the point where I am measuring, that is for the K11, K22, K33 there will be 4 EI by L, and sometimes it will be addition of 4 EI by L plus 4 EI by L, the way we did in the flexibility matrix. So let us try for the some of the examples. Maybe let us take first example where the this is what we have, and we will call it as a 1 and this as a 2. So how to get the stiffness? So what will happen? I will take another color pen if it works. So I will give the unit rotation. So first of all, before give rotation, as we know in the displacement methods, we have to fix, that is restrain everything, and then you rotate it. And then what will happen? You give unit rotation this way, then similar equal and opposite rotation will be generated on the other end. So that will be theta b is equal to 1, theta b is equal to 1. So that's why what will happen here, so K11, that is where I have applied a unit rotation and measuring the moment at this end. So you have to note the way we did in flexibility matrix, here in stiffness matrix also there will be contribution from BA side and contribution from BC, because it is at the junction of two beams. So it will become 4 EI, you can call it as a BA divided by LBA. Okay, 4 EIBA divided by LBA, and then similarly plus what will happen the other side. So it will become again 4 EI BC divided by LBC. Okay, so what will be K12? So what will be K12? If you see K12, because of unit rotation at 1, what is happening at 2? It is 2 EI by L, and related as 2 is here, so you'll have to focus only to the BC span. So what will be K12 is equal to, it will be nothing but 2 EI CB divided by LCB. Similarly, now we will go to the we'll bring back the beam to the original shape. So that is again something like this, and then now we will give unit rotation, instead of at 1 we will give unit rotation at 2. So what will happen here? So it will simply rotate something like this, and then we will call it as a theta c is equal to 1. So what is happening now? So we will have K22. What is K22? It will be 4 EI, what is that? CB, 4 EI CB by LCB, 4 EI CB by LCB. And what is K21? K21 will be again, because of unit rotation at 2, what is happening at 1? So again it will be 2 EI CB divided by LCB, and you can note that K21 is same as that of K12, because stiffness matrix is symmetric matrix. So we'll take maybe one more example, and we will understand, then it will make it clear. So you have to understand that stiffness matrix here, what is the size of stiffness matrix? 2 by 2. What is size of stiffness matrix? Basically 2 by 2. Why this is coming 2 by 2? Because degrees of freedom in this case is 2. So don't consider this was 3, here it is 2. So it will become, K matrix will become something like this: K11, K12, K21, K22. Let us take one more example, so where we have maybe a little complicated example, where we have 3 degrees of freedom. So what will be the 3 degrees of freedom? So if we take this, so we will call it as maybe D1, D2 and D3 and A, B and C. So what will happen here is, like, first I will give maybe unit rotation at A. So what will happen, so you have to fix this, everything I have to first of all fix and then give unit rotation. So if I give theta A is equal to 1, theta A is equal to 1, what will happen, thereafter there is a no rotation this side. So we'll remember 1, 2, 3, and then if you see, you get 3 component by each of this diagram. So it will be K11, that is unit rotation is given at 1 and stiffness is measured at 1. So it will become 4EI AB divided by LAB. Okay. And then what is K12, that is because of unit rotation at 1, what is happening at 2. So it will become 2EI AB, this is in this span only, right, because of the span. So it will be AB divided by LAB, or you can call it as a BA, AB, BA same. But what about C? So do you see any effect of this unit rotation at C? No, because it has not passed from this point, because this end is fixed end. So it has not allowed effect of rotation at A to generate the movement at C. So that's why you can see K13 will become equals to 0. Okay, so I hope I made it clear. So once again, let us take this beam and then give rotation at 2, that is 1, 2 and 3, A, B and C. And then if you give me fix first, you'll have to fix everything and then give unit rotation here, then it will create. So theta B is equal to 1. So in that case, what is happening? So it will create K22. So what is K22? K22 is nothing but contribution coming from BA beam and BC beam. So it will become 4EI BA plus, 4EI BA by LBA plus 4EI BC divided by LBC, right? And then what will, because of rotation at 2, what is happening at 1? So it will become K21. So because of unit rotation at 1, what is happening at 2? It will become 2EI BA or AB, whatever you can call, LBA. So I guess this and this has become same, because it should be a stiffness matrix is always symmetric matrix. And similarly, if you see, because of rotation at 1, rotation at 2, what is happening at 3 is nothing but K23. So what is K23? So it will be 2EI, only thing is span will be different, BC divided by LBC. Okay, so and then similarly we will give rotation at C, last part, that is we will fix all this thing and give the rotation at third span, that is theta C is equal to 1. So as theta C is 1, so you have 1, 2, 3, A, B and C, and then what will happen, K33, what is K33? It will be nothing but 4EI, what is that, CB divided by LCB, 4EI CB divided by LCB. And then what is, because of rotation at 3, what is happening at 2 is nothing but K32 is nothing but 2EI BC by LBC. So can you note now, this and this has come same, of course, for the symmetry purpose. But what happens because of rotation at 3, what is happening at K31? Okay, K31, right, K31. So because of rotation at 3, nothing is happening at 1, so it is 0, and you can see that K31 and K13 are equal, they are 0. So that's how you get 3 by 3 stiffness matrix. So that's kind of clear how to calculate stiffness matrix, step number 3. Let's go to maybe step number 4, that is the joint equilibrium. Step number 4, joint equilibrium. joint equilibrium. So intentionally I am writing, I have not prepared slides so that when you listen my lectures you can also take a pen and notebook and you can write these pointers, because this is kind of mathematical subject. It's not theoretical that you will see the video and just remember it, but you'll have to use pen and paper and note down this pointer. So what is the joint equilibrium? So it will be P total is equal to P plus K into D, and it's very simple. Suppose if it is a 2 by 2, it will be like a 0 0, P total is 0, and then P1 joint loads, so P1 P2, and then stiffness will be plus stiffness will be of course K11, K12, K21, K22, and then multiplied by D1 and D2, and then step number 5, that is we have to get the end movements. Step number 5 is end movements. So we will understand how to calculate the end movements. So time being we'll take the break. So these are 5 steps. Just to recall what are the 5 steps. So there starts step number 0, where we understand the degrees of freedom. So what basically in the beams, at each node there may be maximum 2 degrees of freedom. If it is simply supported, there will be 1, and this will be 0. So that's why here there are 2. Here in this case 0, 0, 1, and in this case 1, 1, 1, that is 3 degree of freedom. So once we understand that, then we go to step 1, where we calculate the fixed end moment. So there are pretty standard formula you can derive it from the consistent deformation methods, etc. Then comes the joint loads. Actually at that joint how many members are connecting, and then it's a kind of combination of fixed end moments of these joints, and then stiffness. So as this will be the size of stiffness matrix will be nothing but degrees of freedom into degrees of freedom. Suppose here there are how many degrees of freedom? 2 degrees of freedom. So it's a 2 by 2 matrix. So here if we take, I guess we have taken another example where we have 3 degrees of freedom, so we'll have kind of 3 degrees of freedom. So once we get stiffness matrix, once we get the through step 2 joint loads, once we get from step 2 joint loads and stiffness matrix from step 3, we can solve these equations, and we get this rotations, that is theta A, theta B, whatever there is a free, and then using these displacements we have to find out end moment. How to do that we will meet in the next lecture. Thank you for your time and patience.